Hi, today I want to make a metal detector, to find silver and gold and the riches of people who just throw them around for me to find. But how do we make one? We Google. What? He just made some gadget to stab metal? That's not it. Maybe this will be the one. Is this sort of metal detecting a thing? So they stick some nail or screw into the wood, wire it to a light, say this one. Then I suppose power it with 120 volts. We plug it in. Well, they're using a battery, but whatever. Then we stab soil with it, and if you're lucky enough to stab a piece of metal, there is just some debris. Oh, okay, now if you touch a metal with these spikes, it shorts between the contacts like a switch, turning the light on. With this rubbish, you only get to search a very small area every time you stab. Oh, at least they are smart enough to use a battery. Absolutely useless. Searching 1 inch at a time, digging would be faster. And yet the video has over 2 million views. Imagine someone uses this to find a landmine. The correct way to metal detectoring is with magnetic fields, as in inductors. And for that, we have to do a bunch of testing using my sponsor Keysight's Tools, who are having a brand new event called Keysight World Innovate. A 3-day free event in which they will cover some future technology. Like in day 1, they'll talk about how we are going to create super speed network highways using 5G and 6G. 6G? Are we pushing the frequencies even higher into the infrared or visible light spectrum, or are we skipping straight into ultraviolet spectrum? I guess we'll learn about it if we sign up from my link in the description, more at the end. So, the magnetic fields generated by an inductor can penetrate deep into the soil and let us know what's going on under it. Like this primary coil of my microwave oven transformer, without the secondary, so no deadly high voltages. If we ignore the deadly 120 volt AC. Anyway, we plug it in. That's why they glue the cord together tight, otherwise it wants to fly apart. And now we can detect metal. My breaker popped. See? If your magnet is strong enough, it can literally pull metal out of the ground. Again, not something you want searching for landmines. And we don't need that much strength, but we need to know how a piece of metal affects the magnetic fields and the inductor itself. And we have to use AC to create changing magnetic fields. Changing magnetic fields create eddy currents in metal, which I talked about in my old video, which would want to push them apart, like you saw in the core. But in ferromagnetic material like iron, the metal itself becomes an even stronger magnet with fields at the same direction as the electromagnet and gets attracted to the electromagnet. But a metal like aluminum that is not ferromagnetic but is paramagnetic, slightly attracted to magnetic fields. No, that's not what I mean. What is antiferromagnetic? Designating or exhibiting a form of magnetism characterized by an anti-parallel alignment of adjacent electron spins in a crystal lattice. What? I guess I can use non-ferromagnetic. Lame. Okay, ferro is iron and ferromagnetic is magnetic like iron. So for any metal that behaves like aluminum, I shall coin the word alumagnetic. So we just discovered aluminum is alumagnetic. Unlike iron that becomes a strong magnet itself due to its atomic structure, aluminum doesn't become a magnet, but the eddy currents generated in it create fields that push aluminum away. A question for you. If you answer it right, I'll heart your comment. Of course, the repelling eddy currents are also created in iron, but the attracting iron magnet is much stronger. The transformer core is iron and should be a very strong attracting magnet. Then why is that they repel each other? Anyway, this is fantastic. It means not only we can detect metal, but also we can tell if they are ferromagnetic or oleomagnetic. Here's the inductor, but this time I'm measuring its inductance. This LCR meter places a voltage across the inductor and measures the voltage and current and calculates inductance and such. And if I place a piece of metal on top of it, well, there is no change. How close should I get? Oh, there you go. Maybe the iron core is focusing the fields too close to the core and very little gets out. I should remove it. But anyway, this piece increases the inductance by around 10% max. Without the core, ooh, seems like the fields are getting a little bit further. Still, it is changing by around 10%. Okay, what do we do with this? Google. Well, this is fake. 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 Fake.
You're watching Keystone Science.
Finally, a legitimate channel. He's creating an oscillator circuit using a coil and a capacitor as its filtering circuit. It makes an audible tone, and when you bring metal close to it, the frequency changes.
If you intend to be finding things in the dirt, with this coil at least, it's practically useless for that.
Yeah, it barely has any range and the frequency barely changes. With a maximum of 10% inductance change, the frequency changes by 5%. And listening to the continuous tone hurts your brain. Hurts. How do we do it then? Well, I have all the information I need, which I saved in a folder and didn't look at. Over 3 years ago, one of my viewers, Carl Moreland, shared with me the book he co-wrote as well as their website, absolutely covering everything about metal detectors, knowledge and design and schematics. Maybe it's time to read it. Wow, this got interesting and complicated in a hurry. Let me do some experiments and make my own simplified version. Let me show you something interesting. I've been experimenting with this coil and different frequencies and such. Well, I placed a coil series with a 1K resistor and I'm supplying some sine wave across the whole thing and measuring across the coil. And if the inductance changes, the voltage across the coil goes up and down. Now I'm supplying 25 kilohertz across the whole thing, and if I just focus on the peak of the signal and bring a pile of copper close to the coil, we will see that copper, due to the opposing eddy currents created through it, reduces the inductance, and so the voltage across the coil drops. And if I bring a piece of steel close to it, we see it increases the inductance and impedance, and so the voltage across the coil rises as expected. Now if I change the frequency to 100 kilohertz, this time we see if we use the copper, the inductance drops again, and if we use the steel, the inductance drops again too. So at 100 kilohertz, we can't really tell the difference between iron and copper. Has something to do with the resonance frequency of iron crystals or something. But it seems like if we use 25 kilohertz, we can tell the difference between ferromagnetic and oleomagnetic material. So we'll use that. I'll keep repeating oleomagnetic until Ward stops putting a red line under it. Here's the plan. I will also make an oscillator using the inductor as its filter. Any metal close to it will affect the inductance and so the resonance frequency. And measuring that, I can detect metal and its type. For my circuit, I'll use the trusty ZVS oscillator. I like this design. With my added current limiter circuit, it is pretty reliable. It can run the coil at around 3 times the supply voltage and runs a ton of current through it without loading the supply much. But I don't like these 2 resistors. They need to have a small value so they waste a ton of power and get hot. In fact, if you know of a good solution for this or a better driving circuit, let me know in the comments. I could heart your comment. Let's make the circuit. I print some sort of coil holder like this. Let's freestyle the coil. I'm using like 26 gauge wire on a 10 centimeter diameter. I'll turn 5 turns first, then I pull out a center tap, then I'll wind another 5 turns in the same direction, like this, a beginning, an end, and a center tap. Per calculations, I can't just wing it. It seems like I have to go with 28 turns with center tap. I think it ended up like 32 turns. Whatever. And here's my circuit too. I'll probably have to readjust some components like the capacitors to hit the right frequency. Here's the circuit running on 9 volts, so later I can run it on 6 AA batteries. This is the voltage across the coil at around 28 volt amplitude. A bit distorted sine wave, because I think I miscounted some of my turns, but that's okay. And this is one side of the coil to ground, and I set the frequency to around 25 kilohertz. So if we bring a piece of iron close, it barely changes. Maybe if we zoom out, we see the frequency drops as iron increases the inductance. And if we use a roll of copper, we see the frequency rises as copper reduces inductance. But the frequency changes very little with these, maybe around 1 to 2%. How do we detect such a small change? Easy! We multiply the sine wave from our coil by another sine wave with a fixed frequency. Filter the result and listen to it. Simple dimple. From the top, multiplying 2 sine waves results in the sum of 2 new sine waves. One has a frequency equal to the addition of the 2 original frequencies, and the other one is the subtraction of the 2. Now, if the 2 frequencies are very close, say 2% apart, which for my 25 kHz circuit means 500 Hz, the resulting sine waves are 500 Hz and 50.5 kHz. We feed the signal into a, say, 1 kHz low-pass filter to get rid of the useless high frequency, and we get an audible frequency. Let's make it! But designing was a different story. Okay, let me save you the hassle. I designed my circuit and tested it on my powered breadboard. Part of my bundle you can buy from my link in the description. First off, we need a stable power supply, so we regulate our 9 volt DC to 5 volt. Then we create an oscillator circuit. I made a Schmitt triggered oscillator and put some potentiometers to fine-tune the frequency. Here's the output of my oscillator circuit, and I can fine-tune the frequency with potentiometer. But wait, it's ugly and it's not a sine wave. That's the beauty of it. It doesn't matter. You may be thinking, how in the world do we even multiply 2 sine waves? Not a problem if you have a square wave. Multiplying 0 and 1 to a sine wave simply means turning it on and off. A square wave is basically the sum of the main frequency and infinite harmonics, which results in infinite sine waves at the output, only one of which is low frequency enough to pass through our filter. Beautiful! And even more beautiful, I don't even need a sine wave from the coil. So what if my signal is half a sine wave and has harmonics? The frequencies of those harmonics will also shift down and my output won't be a sine wave. Who cares? So here's my simple circuit. I take the half sine wave from one side of the inductor through a resistor and use a transistor to short that signal to ground or let it go using the oscillator frequency. And this just multiplies the 2 signals. Then I simply place a low-pass RC to filter the signal at around 1 kHz. Here is the frequency of my oscillator on top and the coil on the bottom, and I tune them to be the same, and if I bring a piece of metal close to the coil, you see that the frequencies start to differ. And the 2 signals are multiplied into the third one on the bottom, as you see. Well, let's look at the filtered. Okay, now the bottom one is filtered and goes up and down. Let's zoom out. You see, the resulting signal can be just a few hertz. Now I realize human ears can hardly hear lower frequencies and not at all below 20 hertz. But we can hear a single very fast click of say 500 microseconds. because a single pulse has many audible higher frequency harmonics. With this, I can make use of frequencies even below 1 Hz. It makes a click, I hear it. So first, I clean up my signal using a Schmitt trigger comparator. Here's the signal on the top, cleaned up and inverted through the comparator. Then pass it through a high-pass RC filter. The edge of the signal going through the RC filter turns into this ramp that has a fixed rate dictated by the R and C values. Pass it through another comparator to make it a pulse. So now these ramps turn into pulses with around 500 microsecond widths. You see if the frequency changes, the pulse width remains the same. And then we can either process these pulses and send them to a headphone, or in my case, I just use a transistor to drive a buzzer. And here's what we hear. We can hear frequencies well below 20 Hz. Done! Here's how it works. First, we tune the frequency to match the frequency of the coil, so we don't hear any pulses. Of course, we should keep all the other metal away. Then we bring a chunk of metal close to the coil. It starts sensing it from like 6 inches away. Of course, the smaller the metal, the less impact it has on the inductance, and it's harder to detect. And here's the roll of copper. Not bad. Let's see if we can detect a quarter. From around 2 inches. How about my ring? Yeah, we can do it. Of course, both types of metal create a frequency difference and sound the same, but to detect the different metals, we can increase our frequency difference, say by lowering the frequency. Now ferromagnetic metal lowers the frequency, and oleomagnetic metal increases the frequency, and very noticeable too. My oscillator circuit though is not super stable. Its frequency drifts a little bit over time, which is okay. We can tune for it using the potentiometer or use a precision oscillator circuit. Good enough though. Now we solder all these components onto the board, which should improve the circuit performance too. Yeah, I'll probably do it later in a short video. I'm just happy it all works thanks to the tools of my sponsor Keysight. Not only Keysight makes some of the most sophisticated test and measurement equipment, but also they hold events to share and discuss knowledge on the leading technology, information and trends. Like the Keysight World Innovate, a virtual vision conference that happens starting June 20th to 22nd. Just a few days away, so sign up now from my link in the description. They will cover 4 topics in 3 days in 2-hour conferences. Like I mentioned, day 1 is about how 5G and 6G will map the information superhighways of the metaverse to take us beyond gaming and transform daily life. Are we going to live in virtual reality? In day 2, go full speed into the cutting-edge advancements in AI-controlled or software-defined vehicles and discover how lessons learned from auto racing can make autonomous driving safer. These sound like a fictional movie is becoming reality. On day 3, we cover non-terrestrial networks and digital healthcare. Learn why extraterrestrial 6G, what is that, is the final communications frontier and how AI-driven devices are transforming healthcare beyond telehealth. Well, these went right over my head. I guess we will sign up to learn what's going on. And thank you for watching.